Hello everybody, this is Jeff with nybbles.io, and this is C11 CKong episode 3, episode 3, episode san, sanban. Okay, so, gosh, lots of stuff. I think I should just show you first off what I have running. We're going to go through all of it. And we're going to then talk about, during that process, forward declarations, and then we're going to talk about pointers to functions and a whole bunch of other stuff. So I'm going to run the app, and I'm going to drag the window over here, and ta-da! There is our game. There's Mario. He's animating. I've got joystick input working. All right. And I got a simple jump. This probably won't be the final implementation for the jump, but it works. And yeah. Lots of stuff. So I want to go through all that, and it's pretty cool. So let's start. Let's go to main.c. So I put headers on all the files now because it's kind of growing up and becoming a real project. So if we look at main, the very first thing that the code does is call game context new. So what is this? So if we go to game context new, this is in the game module, and this allocates a game context T on the stack. It creates a linked list node, which we're going to talk about, for our messages collection. It assigns the controller, which is the joystick controller, to null, and it sets valid to false, and it returns that pointer. So let's take a look at the game context in the header, okay? We have a valid flag. We have a window T structure. We have a pointer to a linked list node structure. And we have a pointer to a game controller structure. So let's try to follow the flow through. So we get a kind of a partially initialized game context. Then we call game init, passing in the context pointer. So then if we flow into game init, this returns a bool. And just so you know, C does not have bool as an intrinsic type. There is a special compiler thing, but it just, they type def it. And then true and false are 1 and 0. And those are type defs. And that's in the standard bool header if you want it. So I guess we don't technically need to set valid to false again here, but it doesn't hurt anything. Actually, we don't need to do... See, this is why you should always walk through your own code. We actually don't need to do either of these. We can get rid of that. So the very first thing we do is we initialize SDL. So we call SDL init, and we pass in SDL init everything, which that sets up the timer, the audio, the video, the events, the joystick, the haptic system, and the game controller system. So everything. If the return value is less than 0, then something bad happened. So then what I do is I set the data element, which is a pointer. So if we go to the linked list node, there's a 32-bit integer key, there's a void star data, and there's a pointer to the previous and next node. That's our linked list structure. And why a linked list? It's just an easy collection type it's an easy, generic, flexible collection type to code up, right? It takes maybe an hour or 30 minutes to code up a decent linked list and test it. And so I went ahead and did that. Obviously, we can use arrays for quite a bit, but I thought it would be nice to have one example of kind of a dynamic data structure, dynamic collection type structure in the system. So since there's only one message in this context, I just assign it to the existing node that's already there using our str clone, which that comes from code that we did in the very first episode. The next thing I do, oh, and we return false if it failed. The very next thing I do is I call an image init. So this is STL image, and I pass in the init PNG flag because that's really all we need is PNGs. If that fails, same thing, assign the message. Then we call window create. So let's walk into window create. So window create returns back a window T, a copy of a window T. So what is a window T? It has a valid flag on it. It has an X, Y, a width and a height, a scale X and scale Y, and it has pointers to an STL window, an STL surface, an STL texture, a messages linked list node, and a renderer. Now notice that I'm using the struct here, and look up here. Notice that I declared STL window, STL surface, STL renderer, STL texture up here. This is what's known as a forward declaration. So what I was trying to avoid including the STL headers in my header. I wanted to keep the STL headers in the module and not in the compilation unit, not in the header file. And the way to do that is to forward declare things. Now, typically for pointers, forward declaration is very easy because the compiler just has to know that it's a struct. It just has to know what type it is that you're forward declaring, and then from there, it knows that that's going to be an 8-byte, 64-bit pointer value, right? And so even though in the C source code we have a nice name here, right? It's a pointer's a pointer, right? But this avoids us having to include the header file. And that's a very common practice. It speeds up compilation time, and it disentangles include dependencies so that you don't have to include things where you don't want to. So that's what a window T looks like. So we create it, we set valid to false, we create a single linked list node and put it on, assign it to the messages pointer, which is a pointer to a linked list node. We set our scale X and Y to the constant scale X and Y, which is 4. So the Donkey Kong arcade, believe it or not, that game is 256 pixels by 256 pixels. That's the dimension of the hardware renderer. To put it on my screen, I've got a 4K monitor here. To make it look halfway decent, I multiply that by 4 so that we get a window that kind of fits nicely on the screen. And yes, it makes the pixels a little bit blocky. If you multiply by 3 here, it makes it a bit smaller. It's not so bad. Screen width and screen height, that's the 256 by 256. We create the STL window. This returns back that STL window pointer. This is the title. This tells STL to center the window on the screen. We take the width and multiply it by the X scalar and the height by the Y scalar. And then we tell STL that this should support OpenGL, this window, and that it should be shown. If that's null, then something bad happens. We create an error message and we return back. The surface I'm not currently using. I put it on here originally because I was experimenting with it. Right now the surface just assigned to null. There's some reasons why having the surface on there, we don't really need it, ultimately, is what it comes down to, because we're using the modern SDL2 accelerated renderer, which puts textures in the hardware and blitz textures using the GPU. So we create a renderer passing in the window pointer. -1 is just this default flag here. And then you tell it that you want the render to be accelerated and that you want to present on the VSync. So this will synchronize to your monitor's refresh rate, and this will use hardware accelerated rendering. If that's null, we have an error message, we return. Otherwise, we need to create a texture. So, and we mark this as a streaming texture because we're going to be updating it every frame. If you had a static texture, then it's intended to be more fixed. Like, so if I had more of if I were uploading the sprites and I were uploading, texture maps to the GPU, and they were just going to render a standard 3D scene, I probably might, want to use a static texture for that because it's just going to sit on the GPU and it's not going to change. But in this case, I'm actually doing pixel twiddling on some surfaces and then copying those to the texture. So we want to kind of make sure the hardware is optimized, set up to allow us to stream changes to the texture without it being a huge overhead. And then we pass in the screen width and the screen height, which again is 256 by 256. So this is, not a huge texture map. We set the render scale quality hint to linear. We don't want STL to burn extra cycles trying to make it look pretty. Linear's fine for this. We set the logical size just to give STL a hint so that when it goes to different DPI displays, it can adjust if it needs to. And then finally, we call STL get window position. Now notice I create some local variables, X and Y here, and I pass the address of those. Why is that? Well, that's because get window position is expecting a pointer to an int for X and Y here. So it wants to populate a piece of memory with that information. So the easiest way to do that is to put X and Y in the stack, pass the address, let it populate that. Then when we get those values out, we assign them to our structure. So now our result, our window T here, we know the X and Y position of the window, we know the width and the height, we know the scaled size, we have pointers to a texture, to a renderer, and we're all good to go. We set valid to true and we return. Okay, so if the window valid flag is not true, we bail. We return false, we're done. Otherwise, we call joystick count. So what's joystick count? This is my wrapper. So I have a game controller module, and this is my wrapper around the STL function, STL num joystick. So this returns an integer of the number of joysticks that are attached to your system. So we take that number, and then we loop from 0 to that number, and we call joystick is controller. So this is a wrapper around another STL function. We pass in the index. So the index is 0 to the number of joysticks, and we say, is this a game controller? If it returns true, then we're good to go. So if it returns true, then we assign the controller pointer on our context, on our game context, to the result of game controller open. So game controller open, we pass the index of the joystick. We allocate our game controller on the heap. We assign the index to the controller. We assign, we call STL game controller open. So this actually connects the STL library to the controller. So now it's actively polling the controller. We get the name for the controller. We get the mapping. The mapping is a string that we can parse later that would break apart, like button A is called this, button B is called that, sort of a thing, right? Because on the PlayStation 4, they have different names for the controllers than like or the buttons than the Xbox, and so on and so forth. So we return back that controller pointer. We break out of the loop because we only need one joystick for this game. Then we call video init. So in the video module, video init creates a surface. So there's a function called create RGB surface with format where STL will create a surface. What's a surface? A surface is just a binary, or I'm sorry, it's just a buffer in memory, RAM, not GPU memory, that is prepped for bitmap display. So there's a structure that sits around it, and then there's raw bytes in memory. And this enum here tells STL, hey, I want a buffer that's formatted as red, green, blue, alpha, and each one of them is 8 bits, right? So it's a 32-byte, or 32-bit value, rather, one 32-bit integer per pixel that is split up as 8 bits red, 8 bits green, 8 bits blue, 8 bits alpha, which is typical, right? We set the blend mode on that buffer to none. We create a foreground surface. So the background surface is going to get updated by the background update engine or update code, which we're going to go through. The foreground surface gets a copy of the background, and then the sprites go on top of it. So every frame, the foreground surface gets reset with whatever is in the background, and the sprites get rendered on top of that, and that gets copied to the texture, which then gets copied to the display. We set the blend mode to none on this, and we enable the RLE engine on this particular surface because there's going to be a bunch of zeros. There's going to be a bunch of repetitive data, and this optimizes the bit blit for this particular surface. Okay, so going back to game, then we call video set background, and we pass in the result of this call, tile map, and we pass in this enum. So if we go to this function, tile map, so I don't know if you remember from episode 2, I went through and showed you all this data that I pulled from my Rust implementation. This is the tile map for the introductory background that you see. So again, as a kind of a primer, right, if you're not familiar with old classic arcade games, the way that the hardware worked is it wasn't really, most of the games, Defender and Robotron were kind of, and some of the Atari stuff were exceptions, but most games were tile-based. What that means is that the screen was divided into subsections, where each subsection was a block, and that block was typically 8 by 8 pixels or 16 by 16 pixels, and then you could create a mosaic, essentially, that would represent the bitmaps that you saw on the screen. That's called a tile map, and typically tile maps have several different pieces of information with them. One is the tile itself. Which tile are you going to put on there? Another piece of information is which palette are you going to use? Because again, these systems, remember, we're back in an era when memory was at a premium, and so I just, in this code, I just went over, did some surfaces that were, 1024 pixels times 4, and that, that's nothing, right? I can create those all day and every day. Back in the day, the processors weren't fast enough and powerful enough to deal with that much data, but B, that amount of RAM is expensive, right? So color information was also grouped into palettes. So you had a palette that typically is of a certain size. In the case of Donkey Kong, there are 64 palettes, and each palette has 4 colors in it. That comes out to 256 colors, but it's broken up into chunks, right? And so you can only assign 4 colors to a tile at a time. So if you look very carefully, every tile is a group of 4 colors. You can't have all 256 colors in one 8 by 8 section, okay? So this data, and then flags, right? So on the hardware, typically there are bit masks that you can set that tell the hardware, hey, when you render this, render it mirrored, horizontally, render it flipped, vertically, and so on and so forth. So this data here represents that tile map, and this has all the data so that for each spot, so 32 across, 32 down, what's the tile number, what's the palette, what's the flags, okay? And this function, this is how we access it. So we return back a read-only pointer to that tile map by indexing into, or by returning the address of that tile map actually. And then the way that you pick the tile map is I have an enum. So I only have one tile map in here right now, but there's actually several. And so I'll be adding more enum entries in here. And then in the module, I will just extend the case statement, and we'll have different static arrays or different static variables here that define each tile map. So if you want to change the tile map, that's active in the video system, you call video set BG. That takes the data from the tile map and copies it into something called the background control table. So now let's look at this video set BG. So I assert that the tile map passed in is not null, and I loop over all the entries in the tile, the background control table. So what's the background control table? The background control table is this static entry, BG control block. So it's an array of BG control block T's for tile map width times tile map height. So 32 times 32 entries in this static array. And so what I do is I loop over that array and I index one for one, and I assign the tile, the flags, the palette, and I actually just realized I guess I really could just do BG enabled and BG changed all in one there. And so this sets the background in the background control. So this is like, you can think of this as the actual front buffer, and the tile map's kind of like a back buffer. We're copying that into there. And then that's kind of our static setup initially. Now this code's going to get refactored because this really doesn't belong here. This is just here for testing purposes. One of the next things we're going to do is we're going to build the state machine that will run the game, and this code will go into a particular state, right, for setting it up. But for now, for testing purposes, this works. Okay, so we set up our video system. We've set our background to the long introduction tile map. Then we're going to get an actor. Okay, so there are three parts to the visual system. There's the background, which we just talked about, which is that tile system. There is a sprite system, and sprites on the Donkey Kong hardware are 16 by 16 pixels, and they can be flipped horizontally and vertically, and they can be assigned any one of the 64 color palettes. Okay, but a sprite is just one tile. It's just one 16 by 16 tile. And in Mario, in Donkey Kong, sorry, I was going to say Mario Brothers. In Donkey Kong, some of the actors or some of the characters on the screen are actually more than one tile. So what I do is I create an actor system that sits on top of the sprite system, allocates the sprites dynamically frame by frame, and allows us to do animation. And it also allows us to do mega characters, mega sprites. So we can put groups of tiles together with different offsets, and we can change those offsets and change the tiles and the flags and the palettes to affect animation at a larger scale. So we go and we ask for the Mario actor from the actor module. So the actor module, or the actor function, takes an actor's T, which is an enum. So right now I just have Mario defined, but we're going to have Donkey Kong, we're going to have, what's her name, Pollyanna, we're going to have actors for barrels and you know, hammers and all sorts of stuff. So to get a particular actor, you pass the enum identifier for that actor. I have a case statement here that returns back the address of the static value that's in this module. So if we come up here and we look at the actor for Mario, here's the Mario data structure. So what does actor T look like? We did this at the end of episode 2. So this shouldn't be too unfamiliar, right? We have the X and Y position for the actor. We have the frame. We have user data 1 and 2. Now I did add some stuff. I added next tick, which is a 32-bit integer. This is for the timer functionality. And I added the actor flags on here. And the actor flags right now are none. I'm sorry, I think we had actor flags before. I just hadn't defined anything in here. So we have none and enabled now, and we might have some additional ones a bit later. We have a pointer to the animation. And then I did create an enum for the different animation types because that's how you select the animation. So we have none. We have Mario standing left and right. We have Mario walking left and right. And we have Mario jumping left and right. So that's what our actor looks like in memory. And this is the initialization we did. So for each static thing, so we're going to have Mario, we're going to have barrels, we're going to have Donkey Kong, we're going to have the girl, I forget her name, we're going to have, you know, whatever we need, fireballs, right? We're going to have a bunch of those actors predefined in here. And then there's an array. So I just have a static array, and I just take the address of each of them and stick them in here, right? So this allows me to loop over all the actors very trivially. But I can still refer to them individually and return the address of those out so that the outside system can get to the actor, okay? Up here, I have animations defined. So the animation for Mario standing left has one frame. Here's the frame array. Here's the structure for the frame. Here we set the delay to 0 because in this case it's one frame, it doesn't change. The tile count's 1. All the Mario stuff is 1 tile. And we have the tile array, and this is the tile entry. So there's no special offset for this, it's 1 tile. It's tile 0 actually, so if we look at the tiles, right, tile 0, this is Mario standing. Everything is to the left, so we have to flip it to the right if we want a right-facing animation. So there's no flip here because it's left. And then Mario's always palette 2. That's what he uses. Standing right is the same thing as left, except we have the horizontal flip. Jump left is 1 frame, same thing. It's tile 14. So tile 14 is right here. There is technically a land frame, and I haven't implemented that. I need to do that. It's kind of a special case at the end of the animation, so I'll have to figure that one out. And then palette 2. Jumping right is the same as jumping left, except we have the horizontal flip flag in place. Mario walking left is 3 frames. So it's frame 0, or tile 0, tile 1, tile 2. Okay? So I have a delay here of approximately 66 milliseconds. We have 1 tile per frame. The offset is always 0 because it's 1 tile. Tile 0, tile 1, tile 2. So about every other frame, we change, about every other V-flip, V-sync, we change the frame to the next frame and it just cycles. So as long as that animation is active, we just keep cycling through the frames until the animation changes and then things reset. Walking right is the same thing, except it has the horizontal flip on it. And that's how we set up animations. That's how we're going to set up all of them. Probably the most complex one will be Donkey Kong and the girl. And that's how that works. Okay, so what we do is we get the actor back, and we set the X and the Y, and then this is wrong. This should be, what should this be? This should be Mario right. Yeah, I think that's what we want. We set the context to valid. We return true. Okay, so that's game init. So if we wind back the stack, we've now made it through game init. Now, if something bad happened, if an error happened, if we couldn't allocate something, I call this log messages function, which is up here. Log messages takes a pointer to a node in a linked list, and it doesn't really matter which node. It'll start at the node that you give it, and it will walk all the way through till it gets to the tail. So it just keeps walking. If the data pointer is set, then we assume that it's one of our stir T structures, and we use our stir print and stir print C to output it to standard error, actually. And then we move to the next node. And we return 1. If it fails, we return 1. And I just realized probably should do this because there. Now the return code is set in both error cases. It wasn't before. So then we call game run, and this is where the fun stuff happens, okay? So we pass in the game context pointer. We have a quit flag that's scoped to this function. We have an Stl event. We have an Stl surface pointer. We get this from the video surface call. So this is in the video module. So remember, in the initialization function, we created a static background surface, a static foreground surface. So this function returns back the foreground surface pointer because the main rendering loop is going to copy this into the texture. So we get that pointer once. We don't need to get it any more than that. We just get it one time. Then we have our main loop. So while the quit flag is not set, we go through this loop. We pull the Stl event queue. If we have the Stl quit message, then we set quit to true. If we have the Stl key down message or event, then we check the key. If it's the escape key, we quit. Otherwise, we don't do anything, and that's it. Then we grab the Mario actor, the pointer to him. Then we check the game controller, passing in the controller pointer, game controller pointer. So this game controller button takes the game controller pointer, takes an enum value, which is defined in the header. So here are all the different buttons that we can check for, okay? And we call Stl game controller get button, passing in the pointer to the Stl controller structure, and we cast our button to their button because numerically they're equivalent. And if it's not 0, then that button has been depressed. And we have a Boolean return type. And so if this is true, so we check for D-pad right. If that's true and Mario's X position is less than 224, we add 2 to it. We clear out the Mario left flag in the Mario actor because now he's moving right and he's running. We set the animation to Mario walk right. Actor animation takes in a pointer to the actor and takes in an animation, that animation structure that we talked about earlier. If the animation on the actor matches the animation we're trying to set, we just return. Because we don't want to reset state. If we're in the same animation, we just want to keep using that animation. Otherwise, we reset the frame to 0 on the actor. We set the animation type on the actor. Then we switch on the type, and we assign the correct pointer based on the animation type to the actor's animation field. Then we set the next tick. So what we do is we take the current time and we add the frame delay to it. And then in the loop, which we'll get to here shortly, we check to see if the timer has passed that tick. And if it has, then we move to the next frame. So that sets our frame. So we check for right, we check for left. So if Mario's X position is greater than 16, we subtract 2 from it. We take off the right flag and we OR in the left and the run. Technically, we don't have to OR in the run again, it's already there, but it doesn't hurt anything to have it there. And then we set the animation to walk left. If we didn't hit right or left, then Mario stops running. We take the run flag off. Okay. Then we check the button. Is button A down? If button A is down and we're not currently jumping, we set the jump flag and we set the jump duration. So there are 2 user data fields on an actor, and we could put more if we needed them. This is 20 frames is the way to think of this. I have a direction integer here, so 1 is left, 2 is right. I use this in an if statement down below. So it's easier to take these bit masks and turn them into an integer so I can use a simple if statement later or ternary condition if I want to. Then I check if we're in a jump. If we're in a jump and Mario's data 2 field is greater than 10, because remember we start at 20, we decrement Mario's Y position. Once we've decremented data 2 down below 10, we start adding back to his Y position. So he goes up and he comes down. We subtract 1 from data 2. If data 2 is 0, we take the jump flag off. Otherwise, based on the direction he was facing last, we set the jump animation right or left. Okay? And that's only 1 frame. It's very simple. And then we check to see if Mario isn't, so if he's not jumping and he's not running, he's standing. So then we set the stand animation again based on the direction that he was facing, right or left. Then we call actor update. So this one's interesting. This is fairly bulky. So first we call video reset sprites, because remember the actor system is built on top of the sprite system. So what does this do? This loops through all the sprites in the sprite control table. And the sprite control table is very much like the background control table that we looked at before. We have a sprite control block structure. It has an X and a Y position. It has a tile, flags, a palette, data 1 and 2. So we loop through, there's 128 of these, because that's how many sprites the Donkey Kong hardware supported. Here. So we set X to 0, Y to 0, tile and palette to 0, and flags to none. So every frame we call actor update. Actor update resets all the sprites in the sprite table, because sprites get reallocated as different actors come and go. So we don't know necessarily which sprite tiles are where, so it's just best every frame to just reset this data, and then the actor system can partition it however it needs to. We have a variable that is the current sprite number. So this is the index into that sprite table. So we start at 0, and we loop through the number of actors we have. So this number here is based on how many entries are in this array. So as we add more actors to the game, this array will get longer, and this number will match that array. Okay? We grab the actor pointer out of the array, and if it's not animating right now, or the animation pointer is null, we just go to the next one, right? So basically, if the actor is in a quasi state or a non-functional state, we don't try to do anything with it. Otherwise, we grab a pointer to the current frame for the current animation on that actor, right? So this is the actor animation pointer. The animation has a frames collection or frames array, and the actor has a frame index on it. right? So we use the actor's frame index to get the frame for the animation that's active on the actor. We have a pointer for that. On the frame is tile count, right? Because remember, each frame is a grouping of tiles, and the tiles can be spread out to make a larger thing. So we loop through the number of tiles. We grab the frame tile from the frame, right? So again, the frame has a collection of tiles, so we're going to loop through those. We grab the sprite, the next available sprite based on the sprite number, and we increment it, right? Because we've used it, now we got to go to the next one. We set the X position for this sprite to the actor's X position plus the frame tile's offset. So again, like Donkey Kong is 4 tiles. So 0, 0 is in the upper left corner of Donkey Kong, right? And you have tile 0, you have 1, 2, 3, 4 that make up that Donkey Kong. So your offsets would be 0, 0, 32, 0, 0, 32, 32, 32, right? Or I'm sorry, not 32. It'd be 0, 0, 16, 0, 0, 16, 16, 16. That's correct. Was thinking about timber. Those are 32 by 32. So that's what this is doing. We set the tile based on the frame tile. We set the palette based on the frame palette. And we set the flags. So whatever the frame tile flags are, and we make sure that the sprite's marked as enabled. And so we loop through the tiles for that frame. We set up the sprites. Then we come down here and we say, okay, if the animation has more than one frame, we're going to then try to move to the next frame. So we grab the current ticks from the STL timer and we say, okay, are we past this actor's next tick? If we are, we increase the frame. And if the frame number is greater than or equal to the max, we reset to the first frame. And then we recalculate the next timeout, because each frame can be different. We can have different timeouts for each frame. So we take the current time that we just got and we add the next frame's delay to it. And so then every time through the draw loop, right, 30 frames a second or 60 frames a second, this code's going to get called. We're checking the timers, and we bump our frames around based on whether or not those times have expired. And that's it. This right here is what allows us to have animating actors on the screen. And they can be really of any arbitrary complexity we want them to be. Then we call video update. So video update calls two functions, video BG update and video FG update. Video BG update, so here's an example of a private function, a static function inside of a module. This is just implementation for inside video. So what does BG update do? So again, we have the static background surface. So we have a buffer in RAM that's not visible. And what we're going to do is we're going to take our tile, our background control data, which represents a tile map, and we're going to set that bitmap. And once it's set, we're not going to change it unless a tile changes. That's an optimization to avoid having to redraw the background all the time, because that's a little bit expensive. So what I do is I call Stl Lock Surface. What does this do? This essentially tells STL, hey, I'm going to touch the internal buffer on this surface directly, and I have a TX and a TY. So this is the current tile X, current tile Y. I calculate the tile map size once up front, so I don't have to do it multiple times. I loop over all the entries in the tile map, so 1,024 entries. I grab a pointer to the current tile that I'm working on. If the tile isn't changed and it isn't enabled, we skip it. I grab the palette entry for this this block's tile, right? So this, again, is very similar to our other stuff. We have a function, takes in an index, and I return the address of one of these palettes here from this static array. If for whatever reason we didn't get a palette, we bail, we keep going. Then I get the tile bitmap for the tile, right? So this, again, this just takes that index and indexes into that array and returns a pointer, returns the address, a pointer, to that array inside of the larger array. So now we have an array to 64 byte, or pointer to 64 bytes, which represent this tile, okay? This 8 by 8 tile. Then I create some convenience variables so I don't have to check the flags every time. I check to see if the H flip is set or the vertical flip is set. Then I set some variables. These are kind of like the, you can think of these as the step variables for the loop, right? Because one loop handles non-flipped, H flipped, and V flipped. So the way it works is we get our starting Y position, our source Y position. If we're vertically flipped, then we go to the bottom of the data, or otherwise we start at the top. If we're vertically flipped, then our delta is to go up lines. Otherwise we go down, we add to the line, otherwise we subtract from the line. Same thing with horizontal flipping. If we're horizontally flipped, we're going to be starting on the right edge of the source data and working our way left. If we're not flipped, we start on the left edge and we work our way right. Then we have two loops. We have a Y loop and an X loop. So Y goes from 0 to the tile height, X goes from 0 to the tile width. Inside of the start of the X loop, I get a pointer, which I just conveniently call P, which is a pointer to the background surface's pixel plus the tile Y start position plus our current Y position times the pitch, right? So the pitch on the buffer is how wide it really is. Because you could say, oh, well, it's 256, but it's 256 times 4. So the pitch represents that unit in there, plus the tile's X start position times 4. Then I set our start X position, our source X position. So if we're horizontally flipped, we're going to start on the right edge. Otherwise, we're going to start on the left edge. I just do this math here to make this line a little bit easier to read. So I multiply our source Y times our tile width plus X. So that's moving a pointer inside of our source data where we're going to read from. Then what we do is we read the pixel from our bitmap, which is really a palette index. So we read that pixel, and then we immediately use that to index into our palette entries, because our palette entry has red, green, blue, alpha information on it. So we get back the palette entry, and then I write the 4 bytes into the actual surface buffer, the bitmap. So I write red, green, blue, alpha. Now in the case of the backgrounds, alpha is always set to 255. We don't allow any transparency in the background. I increment the source X based on the delta. So again, if we're flipped, then this is actually subtracting 1. If we're not flipped, it's adding 1. And then likewise, we change the Y, source Y, based on a delta. So if we're flipped, we're subtracting 1. If we're not, we're adding 1. And so this loops over that tile data and it puts it into the larger bitmap, so that TXTY, right, is moving around and it fills that in. So we take the changed flag off of that block, that control block, because once we put it on there, until something has been touched on the control block to warrant it being updated again, we don't touch it. So we add 8 pixels. I guess technically this should be tile width. This should be tile height, just because I've got constants for it. This is actually screen width. So we add a tile width to TX. If TX is at the end of the screen, we reset TX to 0 and we go to the next line. And then this just loops through all of those tile blocks, those background control blocks, and it renders the background. Once it's rendered into the buffer, then what's going to happen? Well, we're going to have occasionally the score is going to change, or the one-up thing is going to blink, or occasionally it's going to be tiles that are going to turn on or off. So during most frames, we might update, say, 8 tiles, right? So 8 versus 1024. And so that's why this is written the way it's written. We update that bitmap only as things change, only as rectangles are essentially dirtied. When we're done with the loop, we unlock the surface and we do a bit blit. So we take that background, whatever updates we made to it, which again, most frames, this is we're going to pay the piper for this. We're going to loop, but 99% of the time, we're just going to be like, continue, nothing's going to happen. Right? That very first time, we have to pay the piper for everything, but typically most frames, we're not doing a lot of work here. We copy that bitmap into the foreground surface. So whatever the bits are in the background buffer, they get copied to the foreground buffer. Then we call this video foreground update. And this is going to look really similar, because it is. We lock the foreground surface. We loop over all the sprite control blocks in the sprite control table. If the sprite is not enabled, we don't draw it. Otherwise, we grab the palette for it. We grab the sprite bitmap for it, which is the same idea as tile bitmap, except it's 16 by 16 instead of 8 by 8. Same logic here, horizontal and flip flags. Same step logic here, except instead of tile height and tile width, it's sprite height and sprite width. And our loop is the same thing, right? And so, except instead of tile width and tile height, it's sprite height, sprite width. The only difference inside the loop is right here. If the alpha of a palette entry is 0, we skip, right? So to do transparency for sprites, the easiest thing to do was just to check the alpha channel on the palette entry, and if it's transparent, then I just move the pointer to the next pixel in the buffer, and that's it. So again, remember, we copied the background to the foreground. That happens every frame. And then I only put sprite pixels where they're not transparent. If they're transparent, I skip over the pixel that was already in the buffer, so stuff shows through. We take the changed flag off on the sprite. Actually, we're not really using the change flag. This originally, in the Rust implementation, this was because I had separate buffers. I had separate smaller buffers. When I did this one, I'm like, I don't see the reason why I did it that way. So you probably will end up getting rid of this, but it's pretty harmless. I just take the mask off, or take the bit off if it's set. We loop through everything, and we unlock the buffer. And that's video update, right? So that's, believe it or not, for like a game like Donkey Kong, it's like 70% right there, okay? So we've done the video update. Now what happens? We call STL update texture. So remember, we allocated this texture up front, and the reason we're doing that is because the hardware accelerated rendering in STL2 is all GPU texture based. So we have to take that surface, which is a RAM based thing, and we have to copy it into GPU memory. So we use this update texture call. We pass the texture pointer. Null here, this is a rect, an STL rect, but if you want to copy the whole thing, you just pass null. You only need to pass a rect here if you actually are trying to copy a subsection, but we're not doing that. And then I pass the pointer to the pixels for the video surface and the pitch. And then this takes our surface, our foreground surface, copies the pixels into the texture very rapidly. And then we call STL render copy, which copies the texture to the renderer. again, these two nulls, these are the source and the destination rect. If they're null, it just means copy the whole thing. And then we call SDL render present, and this is essentially flip. This is doing the buffering flip in the GPU, or this is actually rendering the scene, you know, from the GPU. And then we loop, and we just keep looping until we hit the quit flag. And then when we hit the quit flag, assuming we return true, we go into game shutdown. Game shutdown calls image quit. This shuts down and cleans up the image, SDL image stuff. If context that's passed in is null, we just bail at this point. Otherwise, we call game controller close, which again checks for nulls here, calls SDL game controller close, passing in the controller pointer. If the mapping was set, we free that with SDL free. You can, the documentation tells you that this is how you have to do this. If the name is set for the controller, we call SDL free on that. Then we just have a bunch of, you know, destroys and frees and things. So if the texture is set, we call destroy texture. If the render is set, we call destroy render. If the window, we call destroy window. We call free on our linked list for the messages on the context. And then we call video shutdown. Video shutdown frees the background and foreground surfaces in the video module. And then we call free on our context, which I should probably do it that way, because we should always free that. And then we return the result code. And that's Donkey Kong up to this point. In C11, debugger is very slow. Come on, Mr. Debugger. Okay. Yep. And so everything we just looked at. So the little Marios at the top, the zeros, the high score, the L01, the ladders, the girders, that's the background. Mario is an actor consisting of one tile frames that are animating based on my state machine here. And it's very simple. Now again, we're going to implement a full state machine that's more full featured than this, because, you know, there's more to, obviously there's lots of little transitions and things that happen in this game, right? So that's what's next. Whew. So I'm sure you guys will have lots of questions about that. All this code is on the develop branch in the CKong repository on GitHub. So you can definitely pull it down, compile it, play with it. So let's talk about pointers to functions. Trying to think of just a really good example here. So int foo int bar is equal to baz int baz int a int b return a plus b. Oh. Okay, so typedef. The typedef for a function pointer is a bit different. This is the name of the type. A little bit bizarre. So I guess being consistent, right? That's probably what we want to do. the C specification, language specification, says that a function label, a function name, is an address as well. So you don't technically have to take the address of the function. You can, for clarity, if you want, but the name of the function itself is sufficient in this case. And so then, if we do bar 22, actually, yeah, just sorry. There we go. Don't even need that. Going to printf C equal D C. There you go. Pointer to a function. And there you go. 4. Pretty easy, actually. And it doesn't, it really doesn't get much more complicated than that. This is the prototype, right? So this is the return in parentheses, pointer, the name of the type, which is, again, this is the type name, not the function name. So I could call this my adder callback T. My adder callback T, right? That's the name of the type. This is the prototype of the function you're calling. So it expects 2 integers. If we didn't have any parameters, it would be void. Right? And then when we call this, you wouldn't be able to pass anything. But if we wanted to pass 2 floats, we'll call it my multiplier callback T 3.14 times 3.14. And this would be F. Oh, and then my return type's wrong. Oh, and the return type on the oh, that's cool. There you go. Now it's right. Yay, type systems. There you go. So, and you can pass pointers here. You can pass anything. You can pass pointers to structures, pointers to base types, whatever you want. Void pointers, you name it. There's no limits here. Any function you can. Any function that's a normal function, you can have a prototype for a pointer to it like this. So this is how pointers to functions work. Now, let's actually do some cool stuff with it. So let's call this state machine. Not the reu header. I really should, I just got to spend the time to configure CLion to contextually generate the right headers, but I just don't spend the time to do it. So in our header file, we're going to do a type def, and we're going to return Boolean, and it's going to, we need standard bool, we need standard int, and we need standard lib. So return bool, and it's going to be state machine callback T, and it is going to take a, what is it going to take? A state context T pointer. Sorry. I got confused myself for a second. All right, so there's our function pointer prototype. And I'm not quite sure what's going to go in the context yet. We'll think about that here as we go along. But we're definitely going to have a state. And that state is, we're going to have an enum so we'll have boot, we'll have attract, long introduction, which we can't, so this is interesting. I probably should mention this, but enums are not a scope in C. These are global, so we need to put little prefixes in front of them to make sure they're unique. Okay, so from memory, that's roughly what states we have. So then in our state structure, we're going to have a states T, state, we're going to have a state machine, callback T, enter, state machine, callback T, update, state machine, callback T, leave. Okay, and so that's our state structure. And state context, I don't know, what goes into a state context? Probably want to have, we haven't defined any of this stuff yet, but we probably want to have the level metadata. It's not a class. So we have level. So there's probably going to be other stuff on the level structure, but for now, I'm just kind of sketching out what I think we're going to have, and then we'll create a player module. Right, and then this is going to have things on it like lives, score, and probably some other stuff, but that gives us at least something to sketch with here. So we're going to have a player T, pointer, right, on state context. So every state, the game loop that we saw is going to call state machine, state update. State update is going to call the right thing based on state transitions. And state update is going to get this state context that's going to come from the game. So we're going to have what are we going to have? I think it's okay here to just define the state context and we can do the same thing here, right? Player T is player 1. Player 1 lives is 3. Player 1 score is 0. We just assign the address of the thing on the stack here. And then we had level. Now level is a bit different because we probably need to get the level from what are you complaining about? That should be fine. Yeah, I mean, technically it does, but yeah, I'm not going to worry about that. So level Okay, so again, just really super sketch, but so other things that you could imagine we would have on the level would be the tile map, tile maps T. So we could do tile map equal tile maps. Or, sorry. This isn't right, but you get the idea, right? Because Donkey Kong has like what, 3 or 4 stages to it. So as we go through the levels, you can change which tile map is active. We can have other metadata on here, like starting positions for bad guys and other parameters for the level. And we can kind of adjust that as we need to, as we go along. So state level is equal to level 0. And I guess, like technically, the player is on the level. from a numeric perspective. So there you go, player 1. So then, as player, we got that kind of roughed out, level roughed out. Let's make sure that compiles. So now in our state machine, we want to, how are we going to do this? So in our module, we need a couple things. We need a static uint8t stack index, and it starts life as 32. And then we have a static state t oh my goodness, state stack 32. It's an empty. Is that what I want? No, that's not what I want. I want an array of pointers. So we start at the top of the stack. We're going to go down, and long introduction, enter, leave, update. What is it complaining about? Oh, because, yeah. So we have to have prototypes. So this, again, this is an example of forward declaration. We have to forward declare these so that the compiler knows that this is actually a function and that the actual body of it will come later. Okay, so that's a setup of a state. So we only have one right now. That's okay. And then what we're going to do, and again, this is the wrong state and all that good stuff. I'm just doing this as kind of, we'll do this in several sections. So I just took all the game update logic and stuff for Mario and all that. What is this complaining about? Oh. Good point. Okay, so we need to, on our state context, we need to put a game controller T pointer on here. We'll set that in the game loop once, because we need to be able to get to the controller device. Everything else is okay. Right, so all that code that was dealing with the joystick and updating the Mario actor and all that, that now is running in the update for the state machine for this state. Now again, this is the wrong state. This would go in the gameplay state, but you know, we'll get there. Okay, so we're going to put some comment blocks, and typically I don't do this, but just to kind of keep these separated, because we're going to have lots of boilerplate in this module, so I want to try to keep it tidy. So in game, we had one other thing, right? We want to move this initialization code into the enter. Beautiful. So now we need a public interface, void state push states t, right? Oh, and one thing I didn't mention, I don't think I've mentioned this, but in C, and this is a little bit of a difference between C and C++, functions that are defined like this are actually variadic functions in C. This is not a void function like you would assume. This, you have to explicitly put void in the function prototype for the parameters in order for it to be a void parameter list. So remember that? That's kind of a little gotcha. Okay. So then what we're going to do is we're going to just replace what we had here before with state long introduction. Right. So in game init, right, do everything we did before. I took the background tile map and the sprite stuff, the actor stuff, and I moved that into the state enter callback. So when you push a state on the stack, it's going to execute the enter. Once the state's on the stack, the top of the stack, update will be called. When you pop a state off the top of the stack, leave is called. And that allows you to clean up, prep, execute, clean up. And so then on our main loop, we want to call state update. And this needs to accept the state context t pointer. And I just realized all of these have to have a context, because if we're going to call the other callbacks, and that's a parameter, it has to be in all of them. Okay. Before I forget, on state context, I'm going to assign the controller pointer. We only need to do that once. And this, we just pass the I'm going to call that state context. It's a better name. So we pass the address of state context into state update. In the push, ooh, that's an interesting one though. Crap. How are we going to do that? Just like that. I have no idea why CLion won't tab these right. I mean, it knows what it is. I mean, it recognizes the syntax, but I don't know, it gets all confused. I think that's okay. I think I'm okay with this because only once we get into game run is the controller necessary. It can be null. I should explicitly set it to null though. Same thing with level. Oh my goodness. Just make sure those are explicitly set to null, because down here, right, we do have the controller. I guess I could set it here. Yeah, why don't we do that? And technically the level should probably be set inside of one of the states anyway. It probably shouldn't be set up here. Like, so when you enter the game state later on, when we get those fleshed out, that's when you would set the level and do all that good stuff. So so when we shut down, we'll pop whatever the last state is off the stack, and we'll be done. That'll give it a chance for it to clean up. Okay. Yeah. Not too bad. Now, how do we do this? So, the first thing we got to do is get the, well, actually, that's actually not right. The first thing we have to do is we have to check to see if sstack index is less than 31. If it is, then that means there's something on the stack. So, so if there's something on the stack, we need to call leave, passing in the context. Right? Because we're going to push something onto the stack. That's going to decrease the index, but we're leaving the state that's there already. So we want to call leave. Then we need to convert the enum into the appropriate pointer. So in this case, state pointer is going to be s long introduction, the address of that. These others we don't have yet, so don't worry about those. So now we have a pointer. So we want to do, just like in a CPU, we want to decrement the stack pointer. We want to make room on the stack. Then we want to, at that location, we want to assign the pointer. Now it's there. So now we want to call enter and pass the context. And that's, oh my goodness. And that's push. Pretty simple. Pop. So if state stack is equal to, or state, I'm sorry. Wow. Stack index is 32. We're just going to return because we're already at the top of the stack. We're done. Otherwise, we're going to call leave we're gonna get rid of it, right? Now we're not really getting rid of it. This is like a CPU stack. I'm treating it that way. I'm not cleaning it out or anything. I'm just moving the pointer around, moving the index around. right? So you pop, if we're already at the top of the stack, or sorry, if the top of the stack is the bottom of the stack, we're done. Otherwise, we call leave on whatever state we're on. We increment the stack pointer, and if we're still not at if the top and the bottom aren't the same, then we call enter on whatever state we just went back to. So you push a state, you push a tract, you push long intro, you push how high. So how high is going to pop itself, and then it's going to push the game. The game's going to finish, then it's going to pop, and it's going to go back to the attract mode, right? And so that's kind of what you want to have happening there. And then state update, or state update is going to check the stack index. If the stack's empty, we don't do anything. Otherwise, we call update, and we pass the context. And there's function pointers. Real live example of using function pointers to do something. And it's pretty simple, in my opinion. So let's compile that. That looks good to go. Let's look at game.c. So in game init, I took out the code that sets the background and sets the actor up. Instead, I push the long state, or the long introduction state onto the state stack. That's going to call enter on that stack, or on that state. See, it's way past my bedtime. I'm doing this late today. So it's going to call the long introduction enter callback. That's going to set the tile map and the background. It's going to look up the Mario actor. It's going to set his position. It's going to set his direction. It's going to return true. We're not handling the return type yet. We'll get to that. If it returns false, then we'll have some bifurcation in behavior. But for now, the simple stuff. And then in the game run, now game run is very agnostic, very simple. It calls state update, passes the address of the state context for the game, and whatever state is active on the stack, is on the top of the state stack, that's the one that's going to get the update call. So let's see how let's see if it works, or if something blows up. Okay, nothing blew up. We got our background, we got our Mario. There you go. Voila. Boing, boing. So there's pointers to functions. We just built a stack, and now we have all the plumbing to finish this game. And so now we can actually start setting up all the states and getting everything to work the way that it's supposed to work. All right, so let's review that. All right, so I'm gonna have to tidy that up. That's a given. So we added a level module, the player module, and the state machine module. In game, I added the static player one, the static state context. I assigned the player, and I null out the level and controller here. The level we're going to end up setting in one of the states anyway. I took out all this, player control code, and I moved that into the state update. And then we call state update now, and whatever state is at the top of the stack, we call update on it. I got rid of some code we didn't need, and I assigned the controller, the gamepad controller pointer, to the controller pointer on the state. And then in the init, we pushed, for now, we pushed the long introduction state just for testing, because that's what we have. This ultimately will push the attract mode state, or the boot state, probably. And then the boot state will push the attract state, and so on and so forth. So, and then in the shutdown, we call state pop to pop off whatever the current, or the last top entry on the stack is, so I can clean up. And then in level, this is brand new. I just created a static level array. We have level number 1, and it has this tile map. I'm not currently using this data, but we will, tomorrow we'll plumb in all that stuff. And then the header file for the level, we have our structure, number, and the tile map, and then a level accessor. In main, I created a local variable for the return code, and I kind of cleaned up this loop, or not loop, these if statements, so that we get the right return code all the time. And then I added player. Player has a number of lives, the current level, and his score. The player module currently doesn't have anything, but we'll add stuff in there. State machine, header file, we have a state context. So this gets passed to all of the state callback functions. So this has a pointer to the level, to the player, to the controller, and we're probably going to end up adding some other state on here too, right? But it gives you basic context information. This is our pointer to a function. This is our callback. It has a return type of bool, and I called it state machine callback t, and it takes in a state context t pointer. I have an enum for my states, and then the state structure itself is which state is it, which identifier, and then the callbacks, enter, update, leaf. And then the public interface for our state machine, we have state pop, state update, and state push. So in the implementation of this, I had to forward declare my static functions for my callbacks so that I could put them in the callbacks here and the compiler wouldn't complain. I have my static definition of the long introduction state. So I assign the enum so we know what it is, and then I assign the enter, update, and leave callback, and we're going to have one of these for every state that we have. Then I have my state stack, which is just an array of 32 entries. And then I have my state stack index, which is one above the end of the array, zero-based, intentionally, because this is kind of like an identifier indicating that there's nothing on the stack. And then we have the actual body of the callback function. So when we enter the long introduction state, so when we push it on the stack, this gets called. We set the background control table to the long introduction tile map. We grab the Mario actor, we set the position, we return true. Then now that state is on the stack, every frame we're going to call update. And so then this is all that code that used to be in the main module or in the game module. Now it's in here, right? And so we get the Mario actor, we check the controller, and we update Mario appropriately. So he does all of his magic. And then theoretically, if we had stuff that we wanted to free up or state we wanted to change, we could do that in the leave callback. Right now it just does nothing, returns true. And then our public interface, so state pop, we check to see if the stack is empty. If it is, we bail. Otherwise, we call leave on whatever the current entry is in the stack. We increment the stack pointer. If the stack is still not empty, meaning we move to another state on the stack after the pop, we call enter on it again, right? Because every time you enter or leave a state, we want to call enter and leave. State update, if the stack is empty, we do nothing. Otherwise, we call update, passing in the context pointer for whatever is at the top of the stack. And when we push a new state on the stack, we check to see if the stack has something on it. If it does, we call leave on whatever is at the top of the stack. We take the enum and we translate that into a pointer to the, because this stack is a stack, it's an array of pointers to the actual states, right? So we take the address of our static long introduction state, we assign that to our temp pointer variable here. We make room on the stack and we assign the new pointer at that location, and then we call enter on it. And that's it for the state stack. And then in the video module, I changed these to be constants because I had them and I might as well use them. And then I tidied up the flags here so it's a little bit nicer. All right. Very nice. I am going to push that up to GitHub. It's on the develop branch. Yeah, so tomorrow I think we'll continue. I probably will do more work on this. If you hadn't noticed, I'm having a lot of fun with this thing because I hate to use the phrase cock blocked. YouTube won't like that, but Rust like really crimped my style. However, again, like retroactively looking back on it, I'm having a much more favorable opinion of Rust now, looking at it in hindsight. And so I think I probably will try to make another game in Rust. Well, I won't do Donkey Kong because I'll have done it, here in C, and I did part of it in Rust. But I definitely think I'll try another one because I think I have, again, a better appreciation for the right way to do it. And yeah, so anyway, any more feedback, by all means, questions, non-pedantic comments are greatly appreciated. And I'll try to incorporate any topics or review any parts of the system. And I would encourage you to pull this code down, try to get it to compile. This code should compile in C Lion on Windows, OS X, Linux, assuming you only need to get the SDL2 dependencies, right? So I'm using SDL2, SDL2 image, SDL2 TTF for now. I will be adding the mixer library in for sound here soon, but I haven't done that yet. So you should be able to get it to compile and run, and read through the code, play around with it, walk through it in the debugger, and if you have questions, by all means, you can post a comment on YouTube. You can join me on my Twitch channel every day, 5 a.m. to 10 a.m., Monday through Saturday. My Twitch channel is twitch.tv/nybbles.io. That's NYBBLESIO. Or if you want, you can join my Discord server. The address, the link to join the Discord server is on my Twitch channel page. And I welcome anybody to jump in there and ask questions. If I don't get any specific feedback on what to cover, then I'll probably just keep working on the game, and I'll just keep going through things like I did, doing heavy reviews and talking about how things work, and we'll just keep fleshing out gameplay and more functionality. I would really like to get as close of a reproduction as I can, right? So I would like to get, the attract mode, the high score stuff, the whole game. So, I'm thinking this is probably going to be like another week's worth, another 6 or 7 days worth of work to get that done. So I think we're probably going to end up with somewhere in the neighborhood of 10, maybe 12 videos for this series. assuming, you know, it's just me finishing the game. If you guys want me to cover specific topics or whatever, we might end up adding another video here or there. Someone did suggest that they would like me to compare and contrast this with C++. I've thought about that. That's going to be kind of complicated. There's lots of little things, right, that are different. Obviously, initializers can be different. There's const differences. There's function prototype differences. But I'm going to think about that some more and see if I can come up with a reasonable approach for how I might do a compare and contrast there. So anyway, I hope this is helpful. Again, this is YouTube only, so I appreciate subscriptions, likes, shares, you know, anything you can do there on the YouTube platform to tell the YouTube algorithm that you love me and you love this content, and I greatly appreciate that. So everybody have a great day, evening, and I will be back tomorrow with another one of these videos. So I will talk with you all then. Bye.